Good day and welcome back to what is now our second video discussing the dot product. So now in the first video we introduced the concept, how do we computationally find the dot product, and we began investigating several of its properties. Most recently we discussed how we can use the dot product to find angles between vectors, and this leads to a concept of orthogonality. So to introduce kind of a new bit of terminology to go with an old idea, we say that two vectors are orthogonal. And note, this is really just a fancy way to say perpendicular to each other if the angle between the two vectors is pi over 2. And note, in a calculus class, whenever possible, we're going to use radians. So pi over 2 radians, of course, corresponds to 90 degrees. So let's think about what that tells us about the dot product going back to this old definition. So if A is perpendicular to B, and remember if we're saying A is perpendicular to B, we're thinking that angle between them is 90 degrees. Then A dotted with B will be the magnitude of A times the magnitude of B multiplied by the cosine of the angle between them. That was this geometric property, or we might think of it as the geometric definition of the dot product. And in this case, the angle between the two vectors is pi over 2. And what is the cosine of pi over 2? 0, you say. That is correct. And in this case, A dotted with B is the magnitude of A times the magnitude of B times 0. And anything times 0 is 0. So a way to state this as more of a property is that two vectors A and B are orthogonal to each other if and only if their dot product is the number 0. And this gives us a really nice kind of consequence of the dot product. We can use it as a tool to check or test when two given vectors are orthogonal to each other. And I'm going to put just a little star here and note that this is an important property. And after we discuss a second product, something called the cross product in 12.4, in 12.5 we are going to talk about lines and planes in 3 dimensions, and this idea is going to come up multiple times. Okay, so the next topic I would like to discuss is something called projections. And I have the kind of book statement of how we define projections, but as we read through this phrase by phrase, we're going to simply just draw a picture to kind of illustrate what's going on. So we're going to let A be a vector going from a point P to a point Q, and B be a vector going from the point P to the point R. So in terms of those vectors, I think we have P, and for convenience, I'm going to draw PQ kind of horizontally, and I'll put R above it, so PR. So we have the vector B and the vector A. Now, in words here, if S is the foot of the perpendicular from the point R to the vector PQ. So what that means is that if we start at R and we bring down this perpendicular, where that hits PQ, we can think of as the point S. Then the vector going from P to S is the projection of B onto A. And how we denote that is we would say projecting, so PROG, and then B onto A. So we think B is the big one, and it projects onto the vector A. And now a little bit of intuition. Why do we call this a projection? So what I'm imagining is that sitting directly above R, we have, maybe a sun, or we have a flashlight that we're shining down. And what this projection vector is actually calculating is the shadow of the vector B cast onto A. And what we would like to be able to do is maybe come up with a formula for what that projection vector is. And in order to come up with a formula for the projection vector, note we know its direction. The projection vector is going in the direction of A. So what we really need to do is determine its length. So I'm going to go ahead and kind of add that down here. I want to write down a formula of the projection of B onto A. And it is made up of kind of two parts. There's the length of that projection vector, and then we need to multiply it by its direction. But we already indicated that we know the direction of this projection vector. It goes in the direction of A. So what we are going to need is the unit vector in the direction of A, and then we'll simply put the length of that vector in front of it. So let's just use a little bit of trig to come up with the length of that vector. And in order to do so, note that we have a right triangle, and in that triangle we'll go ahead and we'll indicate theta as that angle between the vectors A and B. So the observation that we are going to make is if we wanted to find the length of this projection vector, that is the vector we have in red, the length of that vector is going to be given by the length of B times the cosine of theta. And the simple way to see that is, note, if I asked you what is the cosine of this angle theta, in terms of cosine, it's going to be adjacent over hypotenuse. So if we just isolate this adjacent, that allows us to solve for it in terms of B and cosine of theta. But going back to how the dot product is defined in that previous video, the geometric property, how we can rewrite this is we can think of this as being A dotted with B divided by magnitude of A times the magnitude of B. And this is from that geometric, think of it as property, or I'll keep calling it definition, of the dot product. And in this formula, we have what? A magnitude of B divided by a magnitude of B. So the length of that would be A dotted with B all over the magnitude of A. And that's what we need to put in front of the direction. And I'm going to add one small thing here. This quantity with the A dotted with B could most certainly be negative, so it's not necessarily a length, because a length has to be positive by definition. But I'm going to throw one word in front of this. I'm going to think of it as a directed length. If it's positive, it goes in the direction of A. If it's negative, it goes opposite the direction of A. And if we were to take this one step further and simplify it, we certainly can write this as A dotted with B over the magnitude of A squared, a number, times the vector A. And this quantity that represents the directed length, that is what we call the component of B in the direction of A. So this would be A dotted with B, all divided by the length of A. So in words, this is representing the component of B in the direction of A. I.e., in a sense, it's telling us how much of this B vector, maybe if it was a force, this would make more sense, is going in that direction of the vector A. So the length we added above here of PS equals the component of B in the direction of A. All right, so that finishes up the properties that we wanted to discuss in this video. What remains, though, is to look at an example. And once again, if we were in class face-to-face working through this, this is a point where we'd be taking a break and I would be having you work on an example. So what I suggest doing is spending, I don't know, 5 or 6 minutes and see if you can work through parts A and B. So sketch the vectors A and B along with the projection of B onto A, and then find a formula representing that. All right, so now that you've spent a few minutes working through this, let's go ahead and work out the details together. So the first thing I'm going to do is just sketch the vectors A and B. So B is the vector 5, 0. So it starts at the origin and it goes just 5 in that x direction. And remember, whenever we have a vector represented in this component or analytic form, it's a position vector. You start at the origin. The vector 3 minus 4 goes 3 in the x direction, 4 down in the y direction. So roughly speaking, the vector A looks something like this. To find the projection of B onto A, we go to the terminal point of B, and we draw in kind of a line segment that hits A at a perpendicular. And if we look at where it hits A, that's where the projection vector ends. So the projection vector would be in red here. So in red, that would be the vector, the projection of B onto A. So let's go ahead and find this using our formulas, and hopefully when we look back at the picture, our work will agree. So the formula we have for the projection of B onto A, looking above and to the right, would be A dotted with B divided by the magnitude of A squared times A. And these quantities, so A dotted with B, work these out to the side, is 3 times 5 plus minus 4 times 0, which is 15. And the magnitude of A, remember, is the square root of the sum of the components squared. So 3 squared plus minus 4 squared, 9 plus 16 is 25. So we have the square root of 25. And because we want the magnitude of A squared, we quickly see from the formula that's just the 25, which is why I did not simplify it. And this is multiplied by A, so 3 minus 4. And if we simplify just a smidge, this would be, what, 3/5 the vector 3 minus 4. And comparing to our picture that we drew above, that seems fairly reasonable. We're going about 3/5 of the way across that vector A. So that completes the material for this video and most of the properties related to the dot product. What remains in our third and final video, we'll be looking at an application. So stay tuned and take care.